Welcome to This Explainer. Today, we are going to unpack what is honestly the ultimate software blueprint for coding your very own space-time continuum simulator, and we're doing it entirely in Python. If you've ever wanted to somehow smash together theoretical astrophysics and high-level software engineering, well, you are absolutely in the right place. We're going to look at the architecture of an application that bridges the gap between quantum mechanics and beautifully clean modular code. So we're tackling a genuinely fascinating challenge today, one that asks a totally mind-bending question. How exactly do you code the space-time continuum? This source material we're looking at challenges a developer to act as a world-class theoretical physicist, a software architect, and a full-stack developer, literally all at the same time. It's not just about making something that looks cool, right? It's about grounding the most abstract, wild concepts of our universe into executable logical syntax.
Section 1. Designing a time machine, merging code and astrophysics. Okay, let's establish exactly what we're architecting here. The Temporal Architect is designed strictly as an educational tool. It prioritizes hard mathematical grounding over pure fantasy. So no, this isn't some sci-fi video game. It's a rigorously designed Python application that applies real theoretical physics to simulate time travel concepts. And crucially, the prompt mandates that the app explicitly state that real, backward time travel isn't actually possible. It's all about education through simulation. We're simulating the math. We're not promising you a real-life flux capacitor.
Section 2. Science versus speculation. Establishing the ground rules.
Now, as developers of this simulator, we have to draw a really hard line between what we actually know and what we just theorize. On one hand, we've got accepted physics. Things like time dilation, general relativity, quantum mechanics. These are proven realities of our universe, observable and heavily tested. But then, on the other hand, we have these highly speculative concepts. Wormholes, the Alcubierre warp drive, closed time-like curves, which are essentially theoretical time loops. The blueprint dictates that our simulator has to explain exactly which parts are scientifically accurate and which are purely speculative. It's a pretty brilliant way to maintain scientific integrity while still letting users safely explore the extreme edges of theoretical physics right inside a Python environment.
Section 3. The Physics Engine, the core modules.
All right, let's talk about the engine. Our blueprint calls for a production-quality, object-oriented Python architecture built on 6 highly specific modules. Just imagine writing a class structure for a wormhole generator or instantiating a quantum clock. You're also building a space-time engine, a time coordinate system, an energy calculator, and a timeline simulator. Structuring all this using object-oriented programming is absolutely essential. It makes sure that each insanely complex physical concept is totally encapsulated in its own manageable piece of code. You're essentially treating the fabric of reality as objects with properties like mass and velocity and methods like calculating dilation or generating space-time curves. It's just an incredibly elegant way to handle all this mind-bending math.
And here's the kicker. This isn't just some basic script. Every single module has to trace its math directly back to its scientific origins. The prompt specifically demands that you explain every formula with references to Einstein's equations wherever applicable. So every piece of math in those modules we just talked about must trace its lineage straight back to actual physics. To make this truly educational, the developer has to include extensive comments throughout the code explaining these exact connections. The code itself basically becomes a textbook. You're literally coding Einstein's theories and documenting how his equations translate into Python functions. Of course, gracefully acknowledging the reality of software development, this theoretical physics engine still requires standard coding practices, because, as it turns out, even a theoretical wormhole generator needs to pass quality assurance. You still got to write a solid README file, and you definitely need unit tests to ensure your energy calculator doesn't accidentally output negative mass and, destroy the universe. Good code is good code, whether you're building a to-do app or a literal time machine. Now, with that back-end physics engine built and tested, we need to think about how we actually interact with and visualize the universe on a computer screen.
Section 4. Building the architecture, visualizing space-time.
The prompt actually strictly dictates using either PyQt or tkinter for the graphical interface. This gives users a clean, highly functional window to input their environmental data without getting bogged down in overly flashy game engines. But the real magic happens next. We're tasked with using Matplotlib to mathematically render the space-time curvature and the time travel animations. Now, Matplotlib is perfect here because it is completely driven by data and math. This ensures our visual representations of things like black holes and wormholes are deeply grounded in the actual numbers our Python engine is crunching behind the scenes. It completely guarantees the visualization is a true reflection of the physics, not just some artistic interpretation.
Section 5. Simulating the experience. The user journey.
So what does this actually look like for the person using it? The user journey is pretty wild. You aren't just typing dates into a dashboard. You're first feeding the system your exact physical variables. Things like your destination year, your current year, mass, velocity, and the surrounding gravitational field. Once that's all in, the back-end Python engine takes over, crunching those Einstein equations to calculate the massive energy requirements and plot out complex coordinates. And that leads directly to the final educational payoff: watching the system simulate a dynamic visual representation of time dilation, the famous twin paradox, wormhole travel, or even the terrifying gravitational effects of a black hole on time itself. It perfectly connects the abstract math entered at step 1 to a tangible, visual outcome at the end.
As we wrap up this explainer on the Temporal Architect, I want to leave you with a final thought about this newly built simulator of ours. If we can perfectly simulate time travel using exact math to show us the deep past or the far future right on our screens, does it change how we value the present? This prompt really shows us that while we might not be able to physically jump through a wormhole today, we can use clean code, rigorous mathematics, and standard Python libraries to explore the absolute limits of our universe. It empowers us to understand the cosmos in a highly structured, totally fascinating way. Thank you for exploring the fabric of space-time and software architecture with me today. Keep asking those big questions and absolutely keep building the answers.